Hey there, welcome to this next video in this amazing series of Spring Boot where we are learning how we can build a Spring Boot application with the help of Java right from scratch. So if you are new to this channel and if you are watching this video for the first time, then what I would recommend you all is to go to the description and check out the playlist to get access to the videos that were released early in this particular series. This will help you set some context as to what source code is being used in this particular lecture. So coming back to what are we going to cover in this particular session. So we are going to cover Docker. We are going to understand what Docker is, how you can get it set up on your system, what is Docker Registry. We are going to learn about important Docker commands. We are also going to understand how you can containerize our Spring Boot applications. Now, Docker has gained a lot of popularity in past few years, and if you're working with Spring Boot, it's really important that you understand what Docker is and get hands-on with it. So this session will help you do so, and I'm super excited to take you through this journey. Now, as a reminder, if you have not subscribed to this particular channel, I would request you all to hit that subscribe button, like this video, and put on the bell notification. Now, these actions from my viewers just motivate me to bring in more such amazing free content for you all, which help you excel in your career. So without a further ado, let's get started. What's going on, everybody? So in this lecture, we are going to talk about Docker. Now, I would like to teach Docker and give you an introduction with the help of a scenario. And we are going to first understand the problem that Docker solves. And then we are going to discuss what actually Docker is. So let us consider a scenario wherein we have a software development firm and we have two developers working there. So we have Sarah and then we have John. So Sarah is a software developer working on a team that develops a web application. And John is also from the same team. And this team uses a shared development environment where multiple developers work on the same code base. So John is also Sarah's teammate and they use the same code base to push the latest version of the code and also to pull. Now, when working in their code base, they are using several libraries with different versions. Now, let's say John updates a library on his local system. Now, there is a library which has a local version available. So, John updates this library on his local machine and he pushes this code to the shared environment. Now, the shared environment also has the updated version of the library which John has just updated. Now, what happens is when Sarah pulls the latest version of the code, she gets the latest version of the library on her system. And this leads to bugs in her application on her local machine because that version of the library which John has updated is not compatible or does not work on her system because of some environmental issues or some conflicts on her system. So the problem that I'm trying to highlight over here is that the developers are working in a shared environment where library versions and dependencies are not well managed. When one developer updates a library, it can cause issues for others due to version conflicts or compatibility problems. Now, this leads to inconsistencies in development environment and makes it difficult to reproduce the issue or debug them. Okay. Additionally, it brings us to a scenario wherein an application is working fine in one developer's machine but fails in a different environment of other developer. Okay, and this causes frustration and like the team has to resolve these issues and it delays the development process. Now, what is the solution to this? Okay, so the solution to this version is Docker. And to solve this problem, Sarah decides to use Docker. So what she does is she containerizes the application using Docker. Okay, now what this means is, so the code base moves to a container okay, which includes the application code, its dependencies, and the required environmental configuration that is needed for application to run. Okay. Now, this is what the scenario will look like then. So Sarah has the container in which her application is running, and this container is like an isolated environment, okay, which has everything that the application needs to run well on her system. Okay. Now with this, Sarah has no longer to worry about conflicting library versions or incompatible environments or any other issues that may be caused because of any version conflicts. Okay. And this issue which Sarah faced just now, wherein the application was working fine on one of her teammates' machine, but it was not working on her own machine, is something that you as a developer might have also encountered several times. And she decided to use Docker for the same. Okay. Now, what will happen in the team here now is, since Sarah has a container or an image of her code, everybody upgrades to Docker. So we have in the shared environment, we have the code base residing into a container, and also on the John's system, we have a container. So everybody has started using the isolated containers which they can use. And this container has everything that the application needs to run and work well. So to summarize this entire scenario, Docker solves the problem of dependency management, compatibility issues, environmental inconsistency by providing with containerization. Okay. It enables developer to pack their application in and their dependencies into container, and this ensures consistent execution in different host operating systems. Okay. And it eliminates all the version conflicts that were happening early on. So let's define Docker. So what is Docker? So Docker is an open source platform that allows you to automate the deployment, scaling, and management of applications using containerization. Okay. Now, containerization is a lightweight virtualization technology that enables you to package an application along with its dependencies into a standard unit, which is called a container. Okay. And with Docker, you can create containers that have everything that is needed for an application to run. Now, this can include the code, the runtime, libraries, and even the system tools. And these containers are portable, which means you can move them across the systems and can be deployed on any system that supports Docker or has Docker up and running. Okay. Now, this ensures that the same container which is running on my system will work on someone else's system the same way like it was running on mine. And this ensures consistency, and it eliminates this phrase in your team that it works on my machine. I don't know why it's not working on yours. Okay. So this is completely eliminated, and you must have heard this phrase many times, like it's working on my machine. I don't know why it's not working on yours. Okay. So this is completely eliminated and managed with the help of Docker. So this is a Docker container that we spoke about. It has code, the runtime, libraries, and all the system tools that are needed for application to function properly. Now, what are virtual machines? So I want to talk a bit about virtual machine, and we will even discuss how virtual machines differ from that of Docker, because if you have been working with virtual machines, this concept of containerization can be a bit confusing as to how it differs from each other. Virtual machines act as computers inside your computer. So what is a virtual machine? It's a virtual machine that exists on your computer. So you can think of a virtual machine as a emulation of a physical computer system. Okay. So if you have a Windows running on your system, you can run Ubuntu as well on your system using this technique of virtualization. Okay. So it allows you to run multiple operating system and applications within them on a single physical machine, as if you have multiple computers within that machine. Okay. And You can imagine this as a powerful computer and you want to use it to run different operating systems or applications that may not be compatible with each other. So for example, if I want to use a specific software that works only on Linux and I have Windows installed, so I can install Ubuntu as well or any Linux software with the help of virtual machines. Okay, so this technology, virtual machines, will help me create an instance of a Linux operating system on which I can use that application. So that is the problem that it solves. So without virtualization, you will have to buy a separate physical computer or like delete your own host operating system to install the other operating system. Okay, but with virtualization, you can create your instance of virtual machine on your host system. So that is what this means. Like, it acts as a separate computer inside your computer, and each virtual machine behaves like a separate computer. Like I said, it has their own virtual hardware, CPU, memory, storage, and everything. Okay, so it shares some of these resources from the host operating system. Okay, virtual machines are created and managed by virtualization software. So you need a software to create virtual machines, and there are many such softwares available in market. Like, you have VMware, then you have VirtualBox as well. So these softwares provide the necessary things or the infrastructure that you need to run and manage virtual machines on your system. Okay, it also allows you to allocate resources and you have complete control on that. So let's say if you have a 10 core CPU, so you can decide, if you have 5 virtual machines running, I want one core to be allocated to each virtual machine. If you have 10 gigabytes of RAM, you can think of allocating 1 GB each to each virtual machine. So something like that. So it gives you complete control as to what is allocated to which instance of virtual machine, and you can even control their startup and shutdown. Okay, even you can take the snapshots of their state and take backups and restore. So these are what virtualization softwares. Okay, and the advantage of them is they provide a flexible and an easy way to completely utilize your hardware resources. So you can run multiple virtual machines on a single physical machine, saving space, and you can even reduce costs. Okay, so this is what virtualization is. Now let's talk about how Docker differs from virtual machines. So when we talk about virtual machines, this is what the architecture will look like. So you have your machine over here, then you have the host OS, which is nothing but the operating system that you have installed on your system. For example, if I have installed Windows on my machine, so I have Windows as my host OS. Then we have something called as hypervisor, which enables us to create and interact with virtual machines. So once you have these things, okay, you can create virtual machines. So this is one virtual machine that I have created. So it has its own copy of operating system. As you can see, it has all the libraries or binaries that are needed for this particular application to run. Okay, so this entire thing is packaged as a virtual machine, and it will use the system resources that can be allocated to this particular virtual machine using the virtualization software. Okay, so this guest OS can be any OS, like you can install like Linux, or you can install any other instance of Windows as well. Like you can install the same OS as host OS as well. So it's up to you. Okay, so you can have multiple versions of virtual machines running on the same system. So you can have one more instance which runs a completely different app. Okay, and this is in a separate space and a separate environment than this one. So for example, this is running on Windows. Let's say the guest OS is Windows. Here you can install Linux and you can run the app B. Okay, so it will have its own libraries and binaries installed again on this particular thing. You can even run the same app again as a separate instance. So here you have a same instance of app B, or not the same, but the separate instance of the same app B, and you have libs and bins like libraries and binaries installed with any OS of your choice. Okay, so this is what virtual machine is. So you can see like it's a separate computer inside your own computer, which is the host over here. So this is your machine over here. Okay, and you have installed multiple operating systems on top of this, okay, which are running like multiple computers on a single machine. So this is about virtual machines. Now, how does it work with Docker? So with Docker, you have your machine. So this is a machine hardware. You have host operating system, and then you have something called as Docker engine. So this Docker engine is responsible for containers. So you will have like this app. Okay, so this is one container which has application A running. It has all the libraries and binaries. Now, one thing to note over here is it does not have the guest OS. Okay, so this is very lightweight. Okay, so by installing guest OS, you make it a bit heavy. Okay, it needs then high resources and all. But over here, we don't have guest OS. So we don't have an operating system running. So this becomes really lightweight. So it just has the necessary things that are needed for your application to run. That is it. Nothing more than that. Okay. So this is container 1. Then you have another container which runs the app B. And again, this is without the OS. Okay. Then you have the same instance of app B running again as a separate container. So there are 3 containers that are running. Okay. And they are lightweight as compared to the virtual machines that we have over here. And virtual machines become a bit heavy because the entire operating system is installed from scratch as if you're doing a new installation. Okay. So this is about Docker and virtual machines and how they differ from each other. Also, I would want to highlight some of the differences. So I have some parameters over here and I'm comparing virtual machines and Docker containers. So the number one difference is in terms of size. So virtual machines are large and resource intensive. Docker containers are lightweight and resource efficient. Now, the startup time of virtual machines is longer, of course, because a full operating system needs to start. But with Docker containers, almost instant. So the startup is instant as no OS boot is required. So it's pretty quick in startup time. In terms of resource utilization, virtual machines use more system resources like CPU, memory, and so on. But Docker container, on the other hand, will utilize really few system resources. In terms of isolation, there is a strong isolation between multiple VMs because they each have their own operating system. But in terms of Docker container, it is isolated, but it shares the host operating system kernel. That is it. And this is completely fine, I would say, provided that's the requirement. Okay. Then you have the difference of portability. So virtual machines are portable, but they require the compatibility in terms of operating system. And Docker containers are highly portable and independent of host OS. Then we have some more differences, like in terms of scalability. So scaling virtual machine requires creating new VMs. Okay. But with Docker container, it is easy to scale. Like you just need to create more containers. And these containers, like I said, are very lightweight. So when it comes to VM, you need to create highly resource intensive VMs to scale. But Docker is really easy because you are scaling something that is already lightweight. In terms of ecosystem, you need VM specific tools and frameworks. But with Docker, you have Docker ecosystem with a lot of tools out there. Okay. Now, how does development workflow work when you work with virtual machines? So the setup is fairly slower because you are setting up an entire operating system. Okay. But with Docker, the setup is pretty much faster and you need to manage the dependencies for the application that you are running. How is it different in terms of deployment? So in terms of deployment efficiency, VMs are larger in size and they have more overhead. Okay. But for Docker container, it's easier to apply. Like it's easy to deploy Docker containers. All right. So these are some of the differences between Docker containers and virtual machines. So overall, I would say Docker containers are much more efficient, portable, fast, and they're isolated when compared to virtual machines. All right. And that is why this technology is growing really fast and it's becoming very popular in the dev community. So that's about Docker and how it works. I hope you all have a complete understanding of how this particular thing works. And I hope you all enjoyed this explanation. Let us start talking about the Docker architecture and let's understand how Docker works under the hood. By understanding architecture, you will be aware of the important terms and how things are managed behind the scenes. So you have your host operating system, which is your machine OS that you have. So for example, you might have installed Windows or Mac or Linux on your system. So that is what your host operating system is. Then you have these components from Docker, which is Docker daemon, Docker API, and then Docker CLI. Together, they form Docker engine. Now, Docker engine interacts with Docker containers and Docker images with the help of daemon, which in turn interact with Docker registry. Now, what does each component mean and what is their role? Okay, so let us start talking from Docker CLI. So this is a command line interface. So CLI stands for command line interface. It's a client that allows users to interact with Docker. So if you are a user and you want to communicate to Docker, you will execute some commands on the command line, okay, and you will interact with CLI, okay, which is the command line interface. Now, Docker CLI will interact with Docker daemon to get those commands executed. Now, what is Docker daemon? So Docker daemon runs on the host operating system and is responsible for building Docker images and managing containers. So it listens to the user's command via the Docker CLI. And it also interacts with the Docker API and it manages all the Docker objects. So that is what Docker daemon is. Now let us talk about what are Docker containers and what are Docker images. So let's talk about image first. So these are templates with instructions for creating something called as containers. Okay. So you can think of Docker images as a blueprint for creating a container. Okay. So that is what Docker image is. Now from one image, you can create multiple containers. So for example, let's say I have a Docker image for app A. Now for application A, I have already defined a Docker image. So I can create multiple containers using that image for application A. If I want to make any changes to the container, I have to edit the image. So Docker container is a running instance of Docker image. It's a running version of Docker image. That is what a container is. So these two things like Docker images and containers are managed by Docker daemon. Now here we have one more component called Docker Registry. So what is a Docker Registry? So Docker Registry is a service that stores Docker images. Okay. And the images that you store in Docker Registry can be public or private. Okay. So if the image is public, it can be accessed by anyone across the world who is using the Docker Registry. Okay. And if it's private, it's only private to you and no other person in the world can pull those images. So to get the Docker images from the Docker Registry, you have to pull the image and you need to run the image in order to get the containers. Now, if you have a Docker image locally, and if you wish to get that image onto the Docker registry so that you can access it from anywhere, you need to push the image to the Docker registry. So you need to pull the image to get it to your system and push the image to send it to the registry. And all of this is managed with the help of Docker commands. So you can think of Registry as a central repository for all the Docker images. Okay. So the use case of why Docker Registry exists is because the images are meant to share and distribute across different systems. Okay. So this is the internal version as to how the Docker architecture works. And then I have a different version wherein you can see here you have machine, host operating system, and Docker engine. And you have multiple containers that are running different apps with their own binaries and libraries. Okay. And these are all called containers. Okay. So this is how Docker works. And I hope you all have a fair understanding of the Docker architecture and what are different components beneath. So let us talk about and cement the understanding of some of the concepts that exist in Docker. So the number one concept that we'll talk about is images. So Docker images are like templates that exist, or you can think of them like blueprints that define the container and the dependencies that exist within a particular container. Okay. Now, image are the base on which containers are built. So you can say containers are built from images. Then you have containers, and these are lightweight and isolated runtime environments that are created using Docker images. And they provide an isolated and reproducible execution environment for applications. Then you have Docker engine, and this is the runtime that manages the containers. And it provides all the necessary tools and infrastructure that you will need to build, run, and manage Docker containers. Next, let's talk about Docker file. So what is a Docker file? So when you're creating a Docker image, you need to have some sorts of instructions as to what needs to exist in that blueprint. Okay. So that is what Docker file is. So it's a file that contains an instructions to build a Docker image. It specifies the base image, like what all application code that needs to include, the dependencies that it needs to include, and all the other configuration settings. So that is what a Docker file is. Then you have Docker Hub, which is a cloud-based registry that hosts a vast collection of Docker images. You can make use of Docker Hub to share, access, and download public images, and also provide a platform for storing and sharing your own images. So these are the different concepts that exist in Docker. Let us start talking about a bit in depth about Docker Registry. So Docker Registry, like we know, it's a storage and distribution system for Docker images. So you can think of it like a version control system, like a Git you have for source code. Okay, so this system allows you to store Docker images with different versions. So every Docker image that you have, you can tag it with a version name. Okay, for example, if you have a web server Docker image, for example, in your project, so you can say version 1.0, version 2.0, and so on. And these images can be pulled from the registry and deployed onto your server. Okay, so if you have a new version of the image available in the registry, what you and your team members can do is you can access them and deploy onto your server. Now, why do we need a registry? So number one reason will be it acts like a centralized resource for all your Docker images. So if you are working in a team and you have multiple developers, then you will need to access these images. Okay, even if you have servers located at a different location, then someone would be deploying the images over there. So how would you share them? So the sharing of images is made simple with the help of this centralized resource registry. Then it allows for easy versioning. So versioning your Docker images becomes easy. So you can have multiple versions of the same Docker image in the registry, and each version is tagged with a different version number. And this allows you or your team members to quickly roll back to the previous version if needed. Lastly, Docker Registry allows your images to be shared with the public. So if you are working on an open source project and you containerize it, you would want that image to be shared with the public. So you can do that with the help of Registry. So for example, popular databases like PostgreSQL, MongoDB are all available on Docker. Okay, so they have their official images on Docker, and anyone who wishes to use the database, and if they have Docker installed on their system, they can happily use the image and create a container out of that image on their local system. And that will give them a running instance of database without installing the database on their system. So you just pull the container and you just run the container. You have a database up and running. That's the power of Docker and Docker Registry. Now we have spoken enough about Docker Registry, but what are the different Docker registries available and how do I get my image onto them? Okay, so let us take a look at different registries that are available. So here in the browser, I am on hub.docker.com, and this is a default registry that is being used by Docker CLI and most of the Docker tools. Okay, it is a host for a lot of thousands of public images that are supplied by both individual developers and software vendors or big corporations, making it one of the most essential tools for Docker developers. Okay, so here you can see you have Nginx, MongoDB, Alpine, Node.js, Redis, you have Python official. Okay, so there are a lot of Docker images, as you can see. If you scroll down, it talks about the technology. So it says ship anywhere, collaborate, and automate. Okay, and you can scroll up over here. You can create your account as well, and you can search for different images on Docker Hub. Okay, and if you can even click on these images at the bottom, so you can see the image for MongoDB. So you can pull this image, and this is an official Docker image. You can see it's tagged as official one. It has 1 billion plus pulls, I would say. And you can see over here, there are different tags or versions available. So these are the recent tags or versions. Okay, and you can go to the tags page and you can see different tags and versions along with the command. So you have the command as well to get as to how you can get this particular version. Okay, so you can even search for any of your image you want to. So you can say Python, and you will have okay, so there was a spelling mistake here, Python. So you will have a lot of images in and around Python. You have the Python official Docker image as well. Okay, which is insane. So this is the hub. Okay, this is something that you should be aware of. Apart from Docker Hub, you have something from Amazon. Okay, so this is Amazon ECR, or it is called as Amazon Elastic Container Registry. Okay, so if you are using Amazon Web Services for your infrastructure, Amazon ECR also provides the Docker registry as a part of their service. So if you don't want to go outside the Amazon ecosystem, you can use this right on AWS. Okay, and it integrates really well with other AWS services, and it offers a lot of features also. Okay, so you can see the pricing over here. So it has 500 MB of private repository storage per month. So they keep changing this. So you might see something else when you watch this video. Okay, and you can scroll down and read a bit about this tool. Then if you're using Google, okay, like Google Cloud, you can make use of Google Container Registry, okay, which is also known as Artifact Registry. Okay, and it allows you to register and store your Docker images. It integrates really well with Google Cloud Services. Okay, it's a part of Google Cloud infrastructure. So you can read a bit more about this particular tool. Then you have from Microsoft. Okay, so this is Microsoft Azure Container Registry. Okay, and if you're using Azure services, you can use this one if you wish to, and if you wish to stay in the Microsoft's ecosystem. Okay, so this is also a similar registry that is offered by Microsoft. Okay, and you can take a look at how it works. And then you have Quay.io, okay, which is provided by Red Hat. And this is another option. Okay, so it was one of the first Docker registry that existed. Okay, and it still has a lot of features that you can explore. Okay, so this is another option in the market, but Docker Hub is most popularly used right now. Okay, but depending on your requirements, you can choose the one that match for you. So that's about different Docker registries that exist in market. Hello everybody, welcome to this class. So let us start talking about how Docker works with Spring Boot. So initially we'll discuss what all Docker needs to Dockerize an application, and then eventually we'll take this conversation as to how this works with Spring Boot. So to Dockerize any existing application, you need a Docker file. And Docker file is a file that will look something like this. It's a text file that contains a list of commands that Docker daemon uses to build a new image. So each Docker file is a script that has various commands which can be termed as instructions and arguments listed to automatically perform the actions on the image in order to build an image. Okay. So here you can see this is a example file, and now let's debug, or let's go through this entire file and understand what it means. So the first line tells Docker to use official OpenJDK 11 image from Docker Hub as the base image for this image that we are creating. Okay, and this base image includes all the file settings that are needed to run a Java application. Then the next line creates a mount point with the specified path, and it marks it as holding externally mounted volumes. Okay, so this is like a volume that we are creating with the name temp. Okay, then we add the jar file from our target directory to the Docker image. So we have our application ready, and we are assuming that it's ready in the form of a jar file. And we are moving this file into the Docker image, and we are naming it as myapp.jar. Okay. Then we are exposing 8080 port to the host machine, which will allow us to access this application right from our system. So since the application will be running inside a container, we need a way to access our application, and that is what this line will do. And then we have this command, which is entry point, which tells Docker what command to run when the container starts. So when the container starts, we are simply running our jar file. So this is a Docker file. It's an example file, and I'm just giving you an example as to how the file is created. Okay. Now let's understand how Docker works with Spring Boot. So with Spring Boot, you don't need to define a Docker file. Okay, and let me switch over to IntelliJ to explain what I mean. Okay, so here in pom.xml of our application, we have something called as Maven plugin. Okay, so you can see Spring Boot Maven plugin. So we have configured this plugin in our Spring Boot application. Okay, so you can either make use of this Spring Boot Maven plugin that already exists in your Spring Boot application, or you can go with the other approach that I just showed you using Docker file. Okay, so you can either create a Docker file in your project here. Okay, so here in the root directory, you will have to create a Docker file. So you can either create an image that way, or you can make use of Spring Boot Maven plugin. So these are the two approaches as to how Docker can work with Spring Boot. Now, if you're making use of Maven plugin, like everything is automated. So you don't have Docker file, and Docker automatically knows and understands with the help of this plugin as to what all needs to be included into the image for this application to be Dockerized. And that is based on the dependency. So what all is needed is figured out based on the dependency that you have defined here. Okay, and all the properties as well. So on the basis of that, an image is automatically created, and you don't need to set a Docker file. So that's the benefit of using Spring Boot with Docker. Okay, there are less hassles. So how does this entire process work now? So let us talk about this a bit. Okay, so Spring Boot internally leverages cloud native build packs to create Docker images without the need of a Docker file. Okay, now what are cloud native build packs? So this is a specification created by Cloud Native Computing Foundation, which is CNCF. Okay, so this is a foundation that has created this specification, and it is designed to create container images from the source code without the need of a Docker file. So whenever you are using cloud native build packs to create images, the build packs will analyze your project entirely, and they will choose the right tools and libraries for compiling it. So what I mean by right tools and libraries is, for example, you might need a specific version of JDK or for running Java applications. So that is something that it will figure out. Okay, and it will package everything that your application needs into a Docker image. Okay, and this includes determining the dependencies which would all be combined into this image. So you don't have to worry about this. So if you are using Maven plugin, you are actually using cloud native build pack under the hood, because Maven plugin or Spring Boot uses this internally. Then you have Spring Boot Maven plugin. We spoke about this. So this is a plugin that is configured and which triggers the cloud native build packs. Okay, and it packages your entire application into a jar file first, and then it hands it off to the build packs, which will then take it ahead from there. Also, there is a process called layering. So build packs use layering to create separate different parts of the Docker image. Okay, and they call it layers. For example, one layer may have the JVM, and another layer can contain the application dependencies, and third layer may have your application itself. So this allows Docker to cache layers separately, and if you are building Docker images again and again after few changes, so let's say you make one change and then you create a Docker image, and then you do another change and you create one more Docker image. So if you're creating subsequent builds of Docker image, then this layering technique is cache. So all the layers are cache, and it speeds up the subsequent builds that you might create later on. Okay, and this is because you might only change certain parts of the application and not everything. Okay, so it does not need to repackage and redo everything itself again. Okay, so this layering technique helps speed up the process. Then we have something called as Paketo build packs. So the Spring Boot team works closely with Paketo build packs project. So it's a project to ensure excellent support for Spring Boot application. Now, what are Paketo build packs? So these are implementations of cloud native build pack specification, and they provide JVM and other tools required to compile a Spring Boot application into Docker image. Okay. Now, after all of this, we have the result, and the result of the process is in the end is a Docker image. And this Docker image can run in any Docker compatible runtime. Okay. It has everything that your application needs within the Docker image. And this includes JVM, your application dependencies, and your application itself. Now, what is the benefit of using this approach? So the number one advantage is there is no Docker file needed. Okay. So the build packs handle everything that would be normally done in a Docker file, and they do it automatically based on the analysis of your project. Then you get sensible defaults. So the build packs provide sensible defaults for a wide range of project types, including Spring Boot applications. Then you have consistent environments. So this ensures that your application will run in the same environment where it was built. Security. So build packs can keep the base images and libraries they use up to date, which helps in maintaining the security. Layering and efficiency. So the separate layers about which we discussed right now. Okay. These layers can be cached and reused. Okay. Provided that you are changing. So when creating a new image, if you're changing only a particular part of the application, the rest of the layers will be unchanged and they will be reused. So which will increase the speed dramatically, and it will give you images faster. Also with Spring Boot, the process of building Docker image looks really easy, and it's really simple, as so it can be compared to running a single command, okay, or running a simple application without needing to understand the specifics of how Docker images are built. So with Dockerfile, you need to put in the step-by-step information of what all your image will need. But all of this you don't need to do when you are using the Maven plugin and Spring Boot. So that's the benefit that you have. So that's about this class, and that's about how Spring Boot and Docker work together. Welcome back. So let us start containerizing our job application. Okay. So what we are going to do is we are going to make use of Spring Boot Maven plugin features to containerize this application, and we are not going to define the Docker file. All right. So how would you go about this? So we will need to run a command in terminal to create a Docker image. So I have this notepad here, and I have already written this command here. You can see. So this part here, the first part of the command, is about Maven wrapper. So we are using Maven wrapper script. Okay. And this is already included in our project. Okay. It's a script that using which we can execute the commands. Okay. Then we have this part over here. Okay. Which is the Maven goal that is provided by Spring Boot Maven plugin. Okay. And this goal builds the Docker image from the Spring Boot application using cloud native build packs. Okay. So our application will first be converted into a jar file, and then it will be transferred over to the image. And then you have this part here. Okay. This entire piece of code here. So this is a Java system property that is being passed to Spring Boot build image goal. So this is the image goal that we have, and we are passing this entire property to it. Okay. And the D flag over here, like -D, is used to define the system property. So in case you are setting the image name over here, okay, you can set the image name using this particular tag over here. Okay, so you can replace this image name over here, and you can add whatever name you want to. Okay, so the image that will be created with this name. So we will be copying this entire piece of command, and we'll exclude the image name over here. So we'll add the image name later on. But before executing this command, what I would want you all to do is you should switch over to browser, head over to Docker Hub, and create a free account. Okay, so enter all these details like the username, email, password, and agree to the terms and service, like verify that I'm not a robot, and sign up. So once you've created the account, okay, you will be presented with this kind of a screen. So once you have registered, you will be shown this screen. Okay, so you can continue for free. So it's just giving you different options of Docker, and these are paid versions. We don't need a paid version right now, so I'll continue free, and it is asking me to verify my email. So I'll just do the verification. All right, so I'm done verifying my email, and this is the logged in version. Okay, and this is my username, tcode007. Okay, so you can choose the username you want to. All right, so we are done creating the account on hub.docker.com. Now back to this command here. I'm going to copy this part of the command. Okay, and we'll head over to IntelliJ. Now here I'll go to the terminal by clicking on this icon on the left hand side. Okay, and here I'll paste that command. So just make sure that you are in the root directory of the project. Okay, so we just need a terminal. You can run this command even outside IntelliJ in PowerShell or like a normal terminal if you're on Mac or Linux. So the inbuilt terminal should do the job, but make sure you navigate to the root directory of the project. Okay, and I'm going to specify the image name. So I'm going to say tcode007, which is my username, / I'll say job app image like so, and I'll press enter. So we got this error here, okay, and yeah, this says build failure. So there is a possibility that you might get this error. Now, how to solve this is you need to add 2 inverted quotes like for this command, this entire command. Okay, so I'll just copy this entire command here. Okay, and I'll just paste this over here like so, and I'll hit enter. So now you will see a lot of processing that is happening. Okay, so this will take some time, so you will have to wait for a while. Okay, we got another error. Okay, and let me check what this error is. Okay, so this error says that it failed to connect to Docker daemon. Okay, which means Docker is not running on my system. So before running the command, just make sure that Docker is up and running. So I'll just turn on Docker and I'll just launch the Docker desktop that we have downloaded. So Docker engine is starting, because in order to create an image, you need to have Docker up and running. So this will take some time, and once the Docker engine is up, you can go ahead and run the image. So the engine is up. Okay, now I'll go over here. I'll run this again. And now let's wait as to what happens. Okay, so there are no issues as such. Okay, and you can see it has started. You'll see everything on the console. So Paketo build packs. So it's getting the images from Paketo build packs and it is getting the base image. So just take a note of what all processing is happening on the console for a while. Okay, and you can see it's pulling the entire base image of the builder. Okay, and Paketo build packs is something that is used in this entire process of image creation. So this will take some time. Okay, so the entire process is done, and let us take a look at logs and understand what all happened. Okay, so if you scroll up here, you will see a lot of processing that our application went through. Okay, so here you will see a lot happening. So if I scroll up, you will see, so here there were quite a few build packs that were being used, and these were from Paketo. So these were all fetched. You can see the entire fetching that happened. Okay, these were all fetched locally and they were run, and then there were a lot of layers that were created. So if this is a lot of processing, and then if you scroll down over here, okay, you'll see adding layer. So these were all the layers that were created in our application. Okay, so you can see adding layer. This is certificates, and there is one more layer that was created, and so on. Then there's a layer on security, and then there's a layer on config. Okay, there's a layer on image title, image version, the Spring Boot version as well. Okay, so all of this was created, and there was a layer. So there was a layer for a lot of stuff. Okay, so layering happened. All right, and then our Docker image was built. So this is our Docker image that has been built. Okay, and we got this message, build success. Okay, so the image is completely built now. Now what do we need to do? So now we can push the Docker image to the Docker registry. Okay, and how do we do that? So for that we need to run a command. Okay, so we need to say Docker push, and I need to say my username. So my username is decodex, and I need to, so I'll copy this entire thing. So decodex/job app image. Okay, and I'll paste it here. Okay, but I'll also mention one thing. We have not yet logged in from the Docker CLI. Okay, so in order to push images, you need to log in. But let us see what error message we get. Okay, so it says access denied. So I need to say Docker login here. Okay, and it will ask for a username. Okay, so I can say decodex007 like so, and I can give the password. So enter the password and say enter. Okay, and it says unauthorized. Okay, so there is some problem. I'll try again. Okay, so login finally worked for me, and the reason it was not working is because I was entering incorrect username. So it was decode007 and not decode X. So silly mistakes, but that is fine. So I have succeeded to log in onto my terminal, and now I can say we can run the command docker push. Okay, so we have this command. So I'll say docker push decode 007 job app image. Okay, and I'll run this. Now the moment I run this, you will see that everything is happening. So you can see it's going to this repository. So this is my repo against my username, and you can see the image is being prepared and it's being pushed into pieces. Okay, so it will take some time depending on your internet connection speed, but once this entire process is done, you should have your application up and running on, sorry, it won't run. So the image will be up there on Docker Hub. Okay, and you can see that it's done. So let us head over to browser, and here I'll head over to repositories tab here. Okay, so I'll say repositories, and here you can see we have this image here. So if you click on this, you will see this is something that we have pushed right now. Okay, using this particular command. Okay, we didn't specify the tag name. Okay, but we just pushed it. Okay, now we don't have any description, so you can add a description. Okay, and yeah, so you have your first Docker image that you created. Okay, and this Docker image has your Spring Boot application, and it is available on Docker Hub. All right, so that's about this class, and I hope you have your own image as well right now published on Docker Hub. So if you follow the steps that I outlined in the lecture, you should have done this too. So that's about this class. I shall see you all soon. Thank you. Let us start discussing about different Docker commands that exist and are commonly used. Now, I'll mention one thing before talking about Docker commands is this might seem a little bit overwhelming, but don't worry and don't get afraid, because these Docker commands you will eventually learn when you start using Docker regularly. So it might seem like a long list, but actually if you are using Docker in your day-to-day life or when building applications, you will get quite familiar with a lot of commands. So the intent of this lecture is not to tell you to memorize all the command, but just understand like these are the different commands that are available, and this is how they are used. And these all things you can also do with the help of command line tools. So that's the goal. So let's start talking about. So this is the first command that I want to talk about is docker pull. So this command is used to pull the image from the Docker repository. Like let's say we have pushed an image to Docker Hub, and you can use this command to get the image from Docker Hub onto your system. Okay. This command is used to push the Docker image to Docker Hub. So you can specify docker push, then your username /image. This command is used to run Docker container from the image. Okay. So you say docker run, and then you have IT. So I means interactive. Okay. IT stands for interactive. D stands for detach mode. Okay. Detach mode means you can, so basically if you run in non-detach mode, you can't do anything else on the terminal. Okay. And if you close the terminal, the container stops. So if you run in detach mode, it runs as a separate process. And -P stands for port mapping. So you might want to map the port of the container to that of host machine. So you can do that using port mapping. So here you can specify host port and the container port. Okay. And here you are making use of name, and this is the name of the process and the image. Then you have docker stop command, which is used to stop a running container, and you can specify the container ID or the container name. Then you have a command to start a container. So you have container ID and or container name that you can specify. Then you have docker rm command, which is used to remove a stopped container. So if you want to delete a container that has been stopped, you can make use of docker rm. Then you have docker rmi image id or image name. So this command is used to remove an image from a local storage. So images that you create will occupy some storage. So you can get rid of them when you run this command. Then you have docker ps, which is used to get the running docker containers. And this will give you all the containers that are running. Then you have docker ps-a, which is used to show all the containers which are stopped as well as running. Then you have docker images, which is used to list all the images on the host. Then you have this command, which enables you to access a running container. So if you want to log in to a running container from the terminal, you can use this command wherein you say docker exec it and you specify the container name or ID followed by bash, and you will log in from the terminal into that particular container. Then you have docker build -t username image. So this is used to build an image from the docker file. So if you have a docker file defined in the registry in the current directory, so this dot over here specifies the current directory. So it picks up the docker file and creates the image, and the image is created with this name. Then you have docker logs. So this particular command is used to get the logs of a particular container that is running, or a container that exists. So there might be scenarios wherein you might face some issues running the application within the container, and you might want to check the logs. So this command is really helpful there. Then you have docker inspect, which gives you the detailed information of a particular container. So these are all the docker commands that I wanted to highlight. Okay, you can even run these few commands in your terminal and check yourself. So here I am in my terminal within IntelliJ. I can say docker images, and this is going to give you the images that exist on your system. Okay, so here you can see we have created the image for job app. So you have that image. Then you have Paketo build pack builder and run image as well. Okay, which is needed for Spring Boot applications. Then you can say docker ps, which gives you the list of all running containers. So we don't have any running container. Okay, so we didn't get any response over here, but it will give you container ID, image, command, and all the other information. So this way you can try out some of the commands and play a bit. Now let us run the Spring Boot application that exists within the Docker image. Okay, and for that we'll have to run the Docker image. So we already have this image on our local machine. Okay, so if you don't have, you can pull this image from the remote registry and you can make use of docker pull command. So docker pull and the image name will bring you this image onto your local system. But I already have, so I'm going to first copy the name of this image. Okay, and then I'm going to say docker run, and I'll say -p 8080 :8080 space, and I'll paste the image name. Okay, so this is a command that I'm running, and I'll say enter. So you can see now our Spring Boot application is running. So it says started first job application. Okay, so let us understand this command that we just triggered. So we say docker run. This is used to run the Docker image. Then we have -p 8080 :8080. So here we are mapping the port of container to that of the local machine. Okay, so our application will be running on 8080 port within the container, and we are saying like map the port on my local machine to that of the container, because we need to access our application, right? So we are doing this mapping, and once we do that, we run this and we have our application running. Now, if we head over to Postman, and let's say if I try to get the list of all the jobs, okay, we get an error. Okay, now let me see what the error is. So the error has to do with the foreign key where the company ID didn't exist. So I'll try another query where I'll create a company, or I'll create a job. Okay, so I'll create a job, and you can see job added successfully. I'll add it twice, and I'll go to /jobs URL, and you can see I have 2 jobs over here, up here. Okay, so our application is working perfectly fine. Okay, I can get the list of companies as well. Okay, so let me get the list of companies. You can see this is the companies, and you are able to access your application like any other application as if it is running on your local machine. Okay, and that's the beauty. And if you see over here, it's not running in IntelliJ. So IntelliJ application is stopped. Okay, but the problem here is this has blocked our terminal over here. Okay, so if you don't want this terminal to be blocked, what you can do is I'll say Control C over here, or Command C, you can say. It will forcefully stop the application. Okay, and now you can press the up arrow. So this will bring up the previously run command, and it was the run command that we just executed. Now you can run this in the detach mode. So you can say space -d. So you can just add this flag which tells Docker to run this image as a process in the detach mode. So now if you press enter, you'll see that we get this ID over here. Okay, and now if you say Docker PS, so this command lists all the running containers. So if you do this, you'll see you have like this image, and this is the container ID. So this is the ID that we got over here. Okay, so yeah, so this is the ID and the container is running. Okay, you can even get the logs of this particular container. So I can say Docker logs, and I can paste the ID over here. Okay, so you can see these are the logs of our container. Okay, so all the logs are printed over here because we executed this logs command. Okay, so this frees up the terminal, and if you run Docker PS, you can see that it's running as a container, and still you can access your application. So if you want to get the list of all the jobs, okay, you'll get empty list over here. So application is working perfectly fine. It has been containerized, and it's running in Docker container as a process, and we have exposed the port 8080, and we are accessing it through the local host port 8080, and we are able to access it like any other application. So that's the beauty. So yeah, I hope you all have been able to successfully follow these steps and also containerize your Spring Boot application.